the products that we get from the reaction of these various alcohols with um, hydrogen halides like HBr and HCl. And on the board, we wrote the products that we would get. And so we talked about the fact that you would actually get two products in this particular reaction because this has to occur through a SN1 reaction because this is a tertiary carbon. And so when this alcohol gets protonated and it leaves, you end up with a carbocation. And so you can imagine then the chloride coming in from the top giving this product, or the chloride coming in from the bottom of that carbocation and giving this product. And so I gave you a task for this weekend to look at these two products and predict which one would be the major product or the minor product, and to provide a rationale, and that would be due Monday in class if you want to do it for a couple extra bonus points. So something to keep in mind. Another thing that we can do is convert alcohols into alkyl bromides and alkyl chlorides using the reagents phosphorus tribromide or PBr3 and thionyl chloride or SOCl2. And these are really good reagents for doing this. So for example, if you take an alcohol and PBr3, notice the ratio here is 3 moles of alcohol for every 1 mole of phosphorus tribromide, meaning that all 3 of these bromines can actually be utilized. You will actually end up converting the alcohol into 2-bromobutane, plus you end up with phosphorus acid. And with thionyl chloride, you would end up generating the isopropyl chloride or 2-chloropropane. But also you get some byproducts here. You get SO2 and hydrochloric acid. While this is a very efficient process, you do have these byproducts that you have to take into account. So quite frequently you will run this reaction in the presence of a base like pyridine or something to react with the hydrogen chloride that's actually being generated. So these are good reagents for forming alkyl halides from alcohols as well. The mechanisms are fairly straightforward. Now this is showing doing the reaction in the presence of pyridine, which is kind of common, but I want you to know that you can actually do this reaction with thionyl chloride alone. It will do this reaction just fine without too much problem. But again, you don't want that HCl, which is a gas, bubbling out of your reaction and going up the hood and causing a problem. So quite frequently we run this in the presence of pyridine. So if you look at the reaction, the alcohol reacts with the thionyl chloride, makes an oxygen-sulfur bond. This intermediate gets deprotonated by the pyridine, so you end up with a pyridinium chloride. Salt that gets formed. This part that you see here is now a good leaving group, and so the chloride that you have in the system can come in and attack the carbon. That breaks the carbon-oxygen bond and displaces more chloride, and so you end up with SO2. If you look at the arrows here, plus more chloride, which can be used in this next step with another molecule. So this is how the reaction works with thionyl chloride, and so you can imagine that this is kind of like an SN2 type reaction where the chloride will come in from the back and kick out the leaving group, and that's in fact how it behaves for the most part. Similar mechanism for the reaction with phosphorus tribromide. The alcohol attacks the phosphorus. We know that the phosphorus-oxygen bond is really, really strong, and so this reaction occurs very, very readily. And as this reaction occurs, bromide leaves, and so now you end up with this phosphorus-oxygen bond. It's protonated, so the oxygen is positively charged. So now we've got a good leaving group here, and bromide is a pretty good nucleophile, and so what happens now is the bromide then attacks the carbon, the leaving group leaves, and you end up forming the alkyl halide, plus you end up with this phosphorus-oxygen bond. Now this is showing this as if this only occurs once. This species can then go on and react with more alcohol and do the same thing over and over again until you get to that phosphorus acid byproduct. But this is just showing what happens in one step. So again, you don't need a 1-to-1 ratio of the alcohol to the phosphorus tribromide. You need a 3-to-1 ratio, because this is still an active brominating agent and can go on and continue to react. Some general summary comments about the conversion of alcohols to alkyl halides. If you want to make alkyl chlorides, you can use HCl or SOCl2. HCl works really well for the SOCl2 is much better for an SN2 mechanism. So HCl can do both the SN1 and SN2, depends on the nature of the alcohol. So obviously for primary alcohols and methanol, it's going to be an SN2 mechanism. Secondary and tertiary alcohols are most likely going to be, or are going to be, SN1 mechanisms. The conversion of alcohols to bromides, again, HBr works very well, and it can occur through both an SN1 or an SN2 mechanism depending on the structure of the alcohol. Phosphorus tribromide works really well for primary, secondary alcohols. Doesn't work so well for tertiary alcohols, but that's because it actually is involving an SN2 mechanism. Now, if you want to convert alcohols into alkyl iodide, hydrogen iodide works really well for that. Again, very similar to the HCl and HBr in terms of the mechanism. So you need to have all of these things committed to memory. And I would also mention here that you also need to have the Lucas reagent up in this alkyl halide one. So remember, that's the concentrated HCl plus zinc chloride. And that works really well for your primary alcohols because chloride's not a great nucleophile in an SN2 mechanism. And so that helps that reaction out as we discussed on Friday. There's other ways that you can convert an alcohol into a good leaving group. One of the ways to do this is to convert the alcohol into what's known as a tosylate. This becomes what's known as a tosyl group. You can react an alcohol with what's called tosyl chloride, and it reacts very similar in a way that an alcohol reacts with thionyl chloride. It just doesn't immediately convert it into an alkyl halide. And this whole thing that we see here is called a tosyl group or a tosylate. And this is actually a pretty good leaving group. It's somewhere between a bromide and a iodide in terms of how well it leaves. Or like a bromide in a lot of respects. It is abbreviated as OTS. So if you ever see me write ROTS, you need to know that this is some carbon group attached to a tosylate. There are two others that your book talks about, mesolates and triflates. A mesylate, instead of having this aromatic ring here, would just have the sulfur to a methyl group. So no aromatic ring. Oops. No aromatic ring. And a triflate would have a sulfur with a carbon with 3 fluorines on it. And they all give similar chemistry. They all work as good leaving groups. But tosyl is the one that we typically focus on at the undergraduate level. So why is this important? Why not just convert an alcohol into an alkyl halide if you want it to be a leaving group? Well, let's suppose you have a situation where you have S2-butanol. This is a secondary alcohol. And we know if we tried to convert this into an alkyl halide using HCl or HBr or HI, that since it's secondary, it would most likely undergo an SN1 type mechanism, which would give us a racemic most likely would give us a racemic product. And so that's not good because you're taking an enantiomерically enriched or pure product or starting material and converting it into a useless product. But what we can do is we can take this and react it with tosyl chloride. So here's the structure of tosyl chloride. And we can conform the tosylate quite easily in the presence of pyridine. And we know that we start off with the S configuration at this carbon, and we end up with the S configuration at this carbon. So we have just converted the alcohol into a good leaving group without altering the stereochemistry at the chiral center. And so that is very, very important in a number of reactions. And again, tosylates function as good leaving groups, just like the alkyl halides. So anytime you see a tosylate, you can think of them as an alkyl halide, and so you can take a tosylate, you can react it with a good nucleophile. In this case, we are doing an SN2 reaction to form an ether. Very similar to the Williamson ether synthesis here. And they can also undergo elimination. So we could treat a tosylate with a strong non-nucleophilic base. with a strong non-nucleophilic base and get an E2 elimination to form an alkene. So again, they do almost all the types of chemistry that we might expect a alkyl halide to do. So let's think about this particular quiz question. This isn't an actual quiz, but I want you to think about it. So here we're taking an alcohol, a chiral alcohol, 2-butanol. We're reacting it with mesyl chloride, so we got the methyl group. This isn't a tosyl, but it's going to do the same kind of stuff. We're going to react this with an amine base, and we're going to get a product here. And what we're going to get is a mesylate. We've not touched the stereochemistry of the chiral center. And now we're going to treat this with a strong nucleophile. So this nucleophile that we have here. So if we look at this, it's CH3SNA, so sodium, right? So this is a sodium thiolate. So it's sodium plus and sulfur minus. Sulfur minus is, as you know, a very strong nucleophile. So I have a strong nucleophile. I have a secondary alkyl halide with a very good leaving group. This is all going to indicate to me SN2 chemistry. So I would expect that the sulfur would come in from the backside, displace the leaving group, and invert the stereochemistry at that particular product or at that particular carbon. And in fact, that's what we see happens. So we end up with this product. So we start off with this stereochemistry, and we completely invert it because we're going through SN2 type chemistry. So let's talk a little bit about the synthesis of ethers. If you take ethanol, for example, and you react it at fairly low temperature, 140 degrees in sulfuric acid, this is how we actually synthesize diethyl ether, which is a useful organic solvent. However, if you heat it up much hotter than that, you actually undergo elimination and you get ethene. So we can actually take alcohols and convert them into ethers and alkenes by controlling what we're doing with the reaction conditions. And so all of this is using sulfuric acid. Again, I would recommend that you look at the mechanism for these particular reactions. So we will talk about the mechanism on Monday before our inverted lecture. So, but I want you to work on it before you come to class on Monday. So think about that. Now, if we take methanol and tert-butyl alcohol and we react them in the presence of sulfuric acid, we are going to form an ether, an unsymmetrical ether. So the first step, of course, tert-butyl alcohol gets protonated. Whoops, there should be a 2 there. Sorry about that. It should be OH2, and there should be a minus charge there. I don't know what's happening on my slide. And so then we have in the rate determining step where the water leaves, we end up with a tertiary carbocation. That then reacts with the methanol to form the protonated ether, which then gets deprotonated by reacting with some other base. In this case, they're showing the alcohol functioning as the base to deprotonate the ether, and you end up forming the methyl tert-butyl ether, which again is that gasoline additive that you and I that we talked about on Friday. Now, the Williamson ether synthesis, we've already talked a little bit about this. I'm not going to spend a whole lot of time. Your Williamson ether synthesis really works well if your alkyl halide or your tosylate is primary or methyl, because that's going to ensure that we get the SN2 chemistry. Technically, it can work to some degree on secondary alkyl halides and tosylates, but you do have to worry about elimination as well, so one has to pay attention to that. So, for example, here's a couple of examples where we could do some chemistry. And so here we have sodium tert-butoxide plus methyl bromide. We can imagine that giving the methyl tert-butyl ether, but we could also imagine a situation where we have this giving methyl tert-butyl ether. However, the top example is okay. This will work. This isn't a great nucleophile, but it's good enough to displace the bromide in methyl bromide. That's really all it can do here. However, if we reverse this, right, this is a good nucleophile, but this is a tertiary alkyl halide, and so this can't come in from the back and attack the carbon. In fact, the only thing it can do is abstract one of the hydrogens on the beta carbon and give an elimination reaction. So you really want your alkyl halides to be primary or methyl for a Williamson ether synthesis to work efficiently at all. Now we'll talk about protecting groups a little bit in class on Monday before the inverted lecture. So I'm not going to spend a ton of time on it. But what I want to mention briefly is that alcohols can be protected as ethers, and one of the ways to do this is to protect them as a Tert-Butyl ether, where you're taking the OH group, reacting it with this alkene in the presence of sulfuric acid, and you're making this Tert-Butyl ether. And we call this a protected alcohol. It's no longer an alcohol. It no longer has the acidic hydrogen, and so you can protect that, do the chemistry that you want to do, but we also know that this group can come off pretty easily. So let's look at an example where we want to react this nucleophile. So this is carbon minus, right? Sodium plus. We want to do an SN2 reaction on this where this will attack this particular carbon, and this leaving group will leave, making a carbon-carbon bond between these two carbons. That's what we want to have happen. The problem is if you go into the lab and actually do this chemistry, you're going to find that this won't happen because the pKa of this molecule, right, is about 25, 26, and the pKa of this alcohol is about 16. That's a large difference. And so what really happens is this nucleophile won't function as a nucleophile with this molecule. It'll just act as a base and abstract this alcohol or this proton from the alcohol. And so the chemistry doesn't go as you want. So what happens is you end up forming this alkoxide, which is not what you wanted, plus acetylene, which is a gas, and it bubbles out. So how do we force the chemistry to occur where we want the reaction to attack this carbon instead of this hydrogen? Well, we got to get rid of this hydrogen. And so one way to do that, of course, is to protect it. And again, we'll talk more about that on Monday prior to our inverted lecture. So you need to go in and view the slides that I have in Canvas for the material that we should be covering on, or that we would be covering for the inverted lecture on Monday. And you need to read those sections in the textbook before you come to class on Monday as well for the inverted lecture. Have a good weekend.